Hey everyone, welcome to the fourth and the final session of our Training and Fine-Tuning LLMs course. Before we get started with today's topic, please take a moment to introduce yourself in the chat, share where you're joining us from. My name is Darek Kłeczek. I'm a machine learning engineer at Weights and Biases, connecting with you from Warsaw in Poland. And we're absolutely delighted to have a special guest today for the second time, Jonathan Frankle, Chief Scientist at MosaicML, who will be sharing his expertise on training and fine-tuning LLM techniques. Jonathan, we appreciate your presence with us today.
Thank you so much for having me. I'm really excited to be back. Awesome. So should I just go ahead and dive in?
Yeah, sure. Go ahead, please.
Awesome. Let me share my screen and let's get started. So I'm Jonathan. I'm Chief Scientist at MosaicML and now, Chief Scientist of Neural Networks at Databricks. And let's see, hopefully you can see my presentation. Give me a thumbs up. Okay, looking good. So let's dive in. So game plan for today, I really want to do three things. Well, four things. I'm going to start and end with some friendly advice. I gave the same friendly advice last week. So for those, if you're watching the presentation, straight through from last week, you're going to see the same thing again at the beginning and the end. But, I always like to give the same friendly advice whenever I give a talk, so you get to hear it twice. And then we're going to talk about hardware requirements and cost. We're going to actually do some math here. I do want to dig into the numbers and kind of get a sense for, how much it actually costs and how long it actually takes to do some of this training. And then think a little bit about memory and distributed systems and how to actually load these models. And then, when all's said and done, we can actually get into the finer points of pre-training and fine-tuning. I'll actually start by saying one thing, which is I hate the word fine-tuning. I absolutely despise it because I think it's a very poor description of what we do. I've learned to live with it, but whenever I say fine-tuning, I think in my head, the thing you do after pre-training. That thing could be very cheap, like, training on a few tokens, or very, very expensive, like taking a model like Llama 2 and training it on another trillion tokens. And so fine-tuning is often not very fine. And so I hate that word. But I will think of training as divided into two phases. You do a self-supervised, kind of more generic pre-training phase to create a good model for doing a lot of different things. And then you may do many different things to it, which we refer to as fine-tuning, even if they're not very fine at the end of the day. So moving along, again, my friendly advice. Number one, always start small and work your way up. And, I've gone over this in depth already, so I'll just go through it very quickly. Number two, always be skeptical of what you read in the literature and test things for yourself. Number three, don't trust your intuition. Again, test things for yourself. And I just want to emphasize, this is science. You have to run experiments and find out what's going to happen. Okay, so let's talk about cost. So here's how much it costs to train a network in, a nutshell at a very high level. So a flop or a floating point operation is, one computation on, on a GPU or on a TPU or any kind of ML accelerator, usually a multiply add or, something along those lines. And, we approximate by saying that basically all, floating point operations cost about the same thing. And so we look at a GPU and we say, that GPU has 100 teraflops. And so it can do, that would be 100 times 10 to the 12th, or 100 times, times 10 to the 12th operations per second. In that case, floating point operations per second. So, that's a lot of operations, but we also need to do a lot of operations when we train a network. So N here is the number of parameters in the network. And so, we have, the number of parameters in the network times the amount of data. You can think of this as just kind of the number of steps you take during training or kind of the number of forward and backward passes you have to do in the network. Then we got this number 6 in here. And the idea is that essentially, you've got about 2 operations per parameter on the forward pass, and the backward pass is typically twice as expensive as the forward pass because you have to both update the weights and do the chain rule for the next layer back and back propagation. I won't dwell on that too much, but an approximation we often make with transformers is, if you think of it as a fully connected network, the number of flops is approximately 6 times the number of parameters times the amount of data. Now, I said if you think of it as a fully connected network, I'm ignoring self-attention. I'll come back to why we can ignore self-attention a little bit later, but let's just assume this is a basic approximation. Now, the chinchilla scaling laws that I talked about last time tell you that Essentially the amount of data that you should have is about 20 times the number of parameters in the network, more or less. So from this, you can derive a pretty easy formula. Just plug in 20 times n for d on that first line, and you get the number of flops that it should take to train a transformer. So I'm actually going to go through an exercise here. I want to calculate how long it's going to take to train a 7 billion parameter model to the chinchilla amount of data on 64 A100s. And I'm going to tell you that an A100 runs at about 312 teraflops per second. A teraflop is 10 to the 12th. And an H100 is about 989 teraflops, according to NVIDIA. Okay, so I'm about to show a bunch of math. First, chinchilla optimal, that puts us at 140 billion tokens. That's just 20 times the number of parameters. So here's the math. I'm going to go line by line here as I just threw a bunch of numbers up there, so let's take it one line at a time. That first line, I'm just calculating the amount of data. 20 times 7 times 10 to the 9, that's 7 billion. And so that gives us 140 billion. So we can plug that into our flops formula, and we get that our flops is 6 times the number of parameters, 7 billion, times 20 times 7 billion, the amount of data. And that gives us that number on the third line, 5.88 times 10 to the 21. That is a really big number. Okay, so now we can calculate, the number of floating point operations that we can do on this cluster per second, ignoring network costs and any other stuff that might slow us down. So that's 312 teraflops, so 312 times 10 to the 12th, times 64. So that gives us about 2 times 10 to the 16th, flops we can process per second. And then we just divide these two. Take my number of flops, divide it by the flops I can do per second, and that gives me the number of seconds. And so you can see that gives me, 2.94 times 10 to the 5th seconds. That doesn't mean very much to me as a human being, but 3.4 days does. And that's how long this is going to take to train. That's it. Awesome, right? I mean, that's all you got to do to calculate costs. Okay, so there's a little more to this. This was assuming that you were fully utilizing the A100. You were getting all 312 teraflops per second out of the A100. That's never going to happen in practice. There are always going to be reasons that you're not fully utilizing the A100s. And so, we have to take into account the fact that we're not always going to get the most out of the hardware. And so I'm going to add one more number here, which is this MFU number. MFU stands for model flop utilization. And the way to think about it is, how many flops of those available in the chip are you actually using properly? And so the way you can calculate this is you can actually just run the model. We can count the number of flops in that first operation. And then we could just run the model for a while and see how many tokens we're getting through per second. And then from there, you can extrapolate, well, if an A100 is 312 teraflops, and I'm getting this many tokens per second, that many tokens per second, every token I'm doing the number of flops on the first line, and you can divide and figure out what fraction of the max theoretical flops are you actually getting. And that tells you the utilization of the chip. That gives you that MFU number. Now, why not just call it U? Why not just call it utilization or flop utilization? Why M, model flop utilization? So there are a bunch of ways of measuring utilization. If you've ever typed in NVIDIA SMI into your terminal, you'll see, to some extent, kind of a momentary look at what percentage of the chip that you're using. And often it's close to 100%, or, you're seeing some very big number. So it's important to keep in mind that not every operation the chip is doing is actually productive for moving the model forward. I'll give you one example. We're going to talk about memory in a moment, but one thing that can happen is the activations that you compute for the model get so big that you actually run out of memory because you don't have room to store the activations. One thing that people do is they do a procedure called activation checkpointing. They will basically compute the activations and then delete the activations for some layers. That saves you some memory. And then on the backward pass, you can recompute those activations when you have to using the other ones that you saved. This saves you some memory, but it costs you some compute because for some layers you have to do the forward pass twice. That means that some of your flops aren't actually being used productively. They're just being used for recomputation. MFU doesn't take that into account because all you're looking at is the actual flops the model should have taken, that first line, 6 times n. You're not looking at, every single operation that was run on the hardware because many of them are redundant. There's another computation you could do for hardware flop utilization, or HFU, which is in some sense how many actual operations are you doing on the hardware versus how many could it do. We don't like to use that number at Mosaic, and I personally don't like it because it doesn't tell you the story of how productive is training. Anyway, long-winded way of talking about MFUs, but MFU is really, really important. And so that tells us the actual utilization. Now, if I want to go to this link, I'm actually going to go to this link, but this is our MosaicML throughput table. This tells you, what kind of MFU and HFU you should expect to get for a given model on a given hardware at a given training sequence length. This is for, our repository. It, wouldn't apply to any other code base, but it should give you a sense. A typical really good number is around 50%. If you're getting 50%, you're actually doing really well. So, if we go and look this up, the MFU for a 7 billion parameter model on 64 A140 gigabytes for a standard sequence length is about 50.7% MFU. We can then go back and plug that in on that bottom line here, and you can see, well, I'm only actually utilizing 50.7% of the hardware, so my 3.4 days turns into 6.7 days. You can see why MFU is so important. And a lot of people at a lot of places who are building LLMs sweat the details of getting another percentage point here and another percentage point here, because it dramatically changes how long it takes. If you could get this to 100%, you'd have the training time. That would be fantastic. So that's what I wanted to say about training cost. Before I go any further, I do want to pause and see if there are any questions. So Dirk, you can tell me if there are any questions that have come in.
Yeah, there are a couple of questions. I can answer one of them. There was a question about showing weights and biases visualizations. We will not be getting into those details today, but we can definitely take it as an offline follow-up. There is a question if we're going to cover the difference between fine-tuning versus instruction fine-tuning. I think that might be
yes, we'll talk about that a little bit later.
Yeah, there is a question about is it better to fine-tune a smaller LLM for a special use case, or to use like a bigger LLM, a more general LLM? I guess I'm not sure if this is really the right question for this part of the presentation, but if you have any,
I don't know if it's the right part for this presentation, but I'll answer it based on my friendly advice, which is try both. That's really the honest answer. It's hard to know.
Okay, I think we can proceed. Thanks,
awesome. So there's one other thing I wanted to talk about, which is memory usage. So you can start to do some back of the envelope math for memory. So each parameter is typically represented in 16 bits or 2 bytes. So 2 bytes per parameter for the weights. Optimizer state often stores up to 2 full copies of the model, depending on the optimizer you're using, if you need first and second moments or things like that. Okay, that's another 4 bytes per parameter, depending on kind of how large of optimizer state you're saving. You also need 2 bytes per parameter for the gradients. And so we're already at, 8 bytes per parameter. You can do the math. 8 times 7e9, that's, 56 or 5.6 times 10 to the 10th. If you divide that by 1024 to the third, remember when we're converting to bytes, we do need to use powers of 2. So it's not, 1,000 bytes per kilobyte. It's 1024 bytes per kilobyte. Then we get to 52 gigabytes, and you're going to run out of memory on an A140 gig. Okay, that's not good. And keep in mind, that doesn't even include the activations. So we're already in pretty deep trouble before we've even gotten started. Okay, so what do we do? You have to distribute. You have to share across more than one chip. There are lots and lots of ways to do this. So the typical way that we might train on multiple GPUs is data parallel. And I'm stealing some great figures from Colossal AI. They have a nice guide on this. So thank you to our friends at Colossal AI for the figures. And data parallelism is where you have multiple GPUs. You have a separate copy of the model on each GPU, and then you just do different data on each GPU. So then you can average the gradients when you're done. This is not going to work for us because I just said we're going to run out of memory on each GPU. We can't even have one model copy per GPU. So data parallel, nope, out the door. The next thing you can do is something called tensor parallelism, where, so you can see, this is a nice figure from Misha Laskin. So on the left side here is a matrix multiply that we're doing, multiplying matrix A times matrix B. But you can actually split it along the columns and split B along the rows. And in doing so, you can create 4 smaller matrix multiplies. This is a way to save memory. You can actually do, A1 times B1 on one GPU and, A1 times B2 on another GPU, or maybe both on the same GPU, but do A2 separately. And this reduces the amount of memory you need for both, the actual weights that you're working on and the activations that you create. So this is great. There's a much more complicated strategy called pipeline parallelism. This is where you actually have each layer of the network on a different GPU, and you're constantly sending data forward through the GPUs and backward through the GPUs, kind of conducting a forward and backward pass on each GPU, depending on where the data is in the network. And it forms a pipeline. You're constantly passing data forward to the next GPU and back to the previous GPU all the way through as you compute a batch. Pipeline parallel tends to, it's probably the most scalable of these approaches once you take everything else into account, until your layers are too big to even run on a single GPU, and then maybe you make them tensor parallel on a node. The biggest challenge of pipeline parallelism is actually that you get these bubbles. So what happens is when you send through that first batch, all the other GPUs are idle when that first batch is in layer 0. And when the last batch is coming through, the GPUs become idle as you pass through that last batch. So you need to do this on a lot of data before it makes sense, because those bubbles do cost you a lot of utilization. Now, I've mentioned all this stuff, but actually, I want to mention, I said data parallel doesn't work. I actually want to spend some time saying data parallel is great. So I just told you this doesn't work because, as I showed you before, like, I'll go back to that figure. I just said the model's not going to fit on any GPU. So what am I even talking about here? So there's this fancy strategy called zero. And it's actually a set of strategies. But here's the idea. I have all this optimizer state for Atom, but I don't actually need it until the very end. And so while I'm doing my passes on the network, I can actually just take that state and I can shard it. I can break it up into, let's say I'm training on 64 GPUs, break it up into 64 pieces and keep one piece on each GPU. There, I just reduced my optimizer state per GPU by 64x. And if I have more GPUs, it goes down even further. Now, there's a cost to this, that, when I want to update the optimizer, I also have to update it in a distributed way. And when I want to use it, I have to use it in a distributed way. But, sharding that optimizer, that just saved me a bunch of memory. And that's stage 1, what's written here. Then you go to stage 2. You're getting all these gradients. And so, you only have part of the optimizer, so you only need the part of the gradient that corresponds to that. So you can actually share the gradients and kind of split them up and shard them among all the GPUs. That's awesome. That just saved you a ton of memory. Keep in mind, gradients were, 4 out of our 8 bytes. And then, the third stage is that even the model parameters are partitioned around the network. So the idea here, this gets a little tricky, but the idea here is that if I'm using a layer of the network, every GPU has to have that layer, otherwise it can't compute the forward pass. But once I'm done with that layer, I can shard it. I can divide it into 64 pieces and keep one piece on each GPU. And then I need to collect all the pieces of the next layer on every GPU, use that layer, and then I can shard it again. So I can spread the model weights over the entire network, or over all the GPUs. And in doing so, I can almost treat my GPUs like one big shared memory instead of, all these different individual memories. So this process called zero is really, really helpful. The folks at DeepSpeed pioneered a really great implementation of it. Today, we tend to use FSDP, or fully sharded data parallel. This is built into PyTorch. You can just use it right off the bat. I tried to find a snazzy logo, but the folks haven't created one for FSDP yet. So if any of the FSDP creators are listening right now, you could definitely use a snazzy logo. But we love FSDP at Mosaic, and it's integrated very deeply into our LLM Foundry. This is our kind of default way of training networks. We'll use FSDP at scale, and that's allowed us to scale up to hundreds of billions of parameters and thousands of GPUs. So, and hopefully beyond that. So that's really, when it comes to distribution, I think that's pretty much everything you need to know about training time and flops and memory and cost and utilization, and then how to actually distribute it. I want to pause again to see if there are any questions or comments that people want to throw in.
Yeah, we have a couple of questions. There's actually a request from some of the audience about the quality of the audio. So if you can check, Jonathan, if there's any applications that you can close, I think that would be
everything should be closed.
Okay. For those that have a hard time following, the recording that we will post afterwards should have like all of the audio issues fixed. So at least if you bear with us for some time, like we'll make sure to upload the high quality video. But hopefully it works at least for some of the audience. I will post another question in the chat as well. I'm gonna read it. The chinchilla loss estimation don't take into account many hyperparams and choice of architecture for the model. Thus, also not the inductive biases allowed by the training setting. Do you think it's an overly gross estimate of the loss?
So it's the crux of the question is like all this chinchilla stuff, it's a rough estimate. It doesn't take into account a lot of stuff, and it may vary in every setting. So can we trust it? And the answer is, well, no, we can't trust it. But I challenge whomever asked the question, can you do better? Do you have enough GPUs to do better? Do you have enough GPUs to, go and do this for a wide swath of hyperparameters, or do it for a different model architecture? So in some sense, it's not perfect, but it is a really helpful approximation that gives us some guidance on what to do. And it's the best we're going to get, to be honest. And if you wanted to redo this in every setting, you'd be training so much that you'd have to train the network you wanted to train and 100 others or hundreds or thousands of others in the process. And so it's just not feasible in practice. So yeah, and what's the famous quote? All models are wrong, some models are useful. Chinchilla is a very useful model that is completely wrong. It's a great question.
Appreciate it. Maybe one more question from me. We see all of your example actually based on A100s, and it seems like everyone is training these models on A100s. How about some of the older GPUs that might be more available, like V100s or T4? Maybe does it make sense to consider them for training or fine-tuning LLMs, or do they have some deficiencies and we should default to A100s?
It's a great question. So V100s are excellent GPUs. They're thoroughly outmoded at this point compared to the latest stuff. If I recall correctly, a V100 will get you, I'm trying to remember the exact number of teraflops for a V100, but nothing that will blow your mind today, but what blew my mind back in 2017. I'm now actually Googling it. A V100 has 130 teraflops. So it is about, an A100 is about 2.5 times more. And an H100 is, what is that, about 6 times more? 7 times more? So you're in a place where, in some sense, if you told me I could have any GPU I wanted, and you told me the prices and, based on the prices I tend to see on marketplaces, I would I would look at those prices and say, wow, V100 is not really that competitive because modern GPUs are just so fast. But, if you have nothing else, a V100 is still an excellent GPU and you can get a ton of work done. So, definitely not a bad thing. The biggest trickiness with V100s is actually if you wanted to do a multi-node training job, if you want to go more than 8 GPUs. If you wanted to do that, you'll be in a very tricky place because many of the V100s were not built with very high bandwidth between them. It just wasn't the days of doing this large-scale multi-node training in the clouds. And, nobody's upgraded that because they've moved on to new things. So you'll end up in a place where things may get a little slow if you try to do multi-node training. But at the same time, still an excellent GPU. When you get to things even older than that, things start to get very tricky. The V100 was the first mainstream NVIDIA GPU that had tensor cores, and the tensor cores are built for things to run really, really fast. If you go back to, say, a P100, you'll no longer have those, and things get tricky.
Thank you.
Awesome. Any other questions we should cover? Or should we keep going?
I think we should keep going. Thank you.
Awesome. So now we get into the question of architectures. What should you train? And I'm going to give you more questions than answers in the spirit of test things yourself and don't believe what you read. First, architecture sizes and scaling are pretty standard. We have standard ways to increase the number of layers or increase, the width of the network as we scale up. You can kind of follow the best guidance from, the Chinchilla paper or the OPT paper or what the Llama models did. There are a lot of excellent references where those folks did their homework and, we can trust largely what they found. At least, not very many of us have the number of GPUs necessary to go and question what they found and try to do better. But there is a trade-off between training and inference costs, and this is where Chinchilla kind of comes back. You have to take into account, well, how fast do you want inference to be and how much work is happening at inference time? You could train a Chinchilla optimal model, But that model may not be optimal for inference, depending on, if you've got a lot of inference queries, you actually want a smaller model. It'll do inference more efficiently, it'll be lower latency, it'll be cheaper to run. And in that case, it might actually be worth your time to train a suboptimal model at training time, to train longer on a smaller model. This is exactly what the Llama folks did. That was kind of the revolution to me of the paper. They trained for a very long time on some small networks and still got pretty good results, even if they were suboptimal compared to what they would have done if they had spent the compute perfectly for training. But the networks became really popular, in my view, because they were easy for anybody to use at home and do inference on. You could do it on your gaming GPU. That was a big deal. And so really, at the end of the day, your architecture choice involves this trade-off you need to make between, how much you want to spend for training, and are you willing to actually spend a little bit more for training to get cheaper inference? And that's a trade-off you can then calculate. The next big decision you have to make is sequence length. Sequence length is tricky. Longer sequences increase the cost of attention because, the self-attention operation is quadratic. If you have a longer sequence, then the model needs to attend, every token has to attend to every token. And so you end up paying this very big penalty. And, it gets quadratically worse as you increase the sequence length. Now, it's important to note that with some modern, techniques like flash attention, I won't talk about flash attention, but it's just a fast way to do attention. The attention costs are relatively small compared to the overall cost of using the feed-forward layers in a transformer network. And so you end up in a place where actually, you'll see before, I didn't even take attention into account when I was computing the flops, because attention is so negligible and so fast compared to all the other fully connected layers in the network. So, eventually you get long enough sequences that attention cost does actually start to matter. And it's kind of interesting. If you look at some of our throughput tables, you'll see something pretty remarkable. As you get to really big networks, there's basically no penalty for having longer sequences because the cost of attention is completely drowned out by the cost of the bigger network. For a 30 billion parameter network, I believe there's no penalty in going from sequence length 2048 to 4096, and only, if I recall correctly, a 15% penalty in going to sequence length 8192. That's not too bad. That's, a price potentially worth paying. For a 7 billion parameter network, the kind of relative price to you escalates pretty quickly because the rest of the network is so much smaller. Then you get into a question of, just data. Do you have enough data to use a longer sequence length? It's a tricky question. We found that in a lot of the standard data sets that are out there, there just isn't a lot of long sequence data. So if you wanted to train a long sequence model, you may not have much to work with. And even if you did have stuff to work with, you have to be very careful where you pull it from. If you try to kind of sample from all your data sets evenly, some data sets don't have any long sequence data, and you'll see the same few examples over and over and over again. Then we get into one last open question. I think this is more of an open scientific question right now. Just because we can cram really long sequences into memory does not mean the model's actually taking advantage of them. Just because you can get the bits from point A to point B doesn't mean that, you're able to, actually use them in an effective way. The model may not be able to learn or may not be able to holistically take advantage of all that information. And I think that question's still out there. We still have a lot to learn about long sequence training. So there are so many other choices. I'm not going to go through every single one. I lumped all these choices together into one slide. I'm going to go through them, but I lumped them together because I don't think there are clear answers to any of these. Positional encodings, how you represent, which token is in which part. There are lots of different methods. The two most popular are rotary embeddings or ROPE, rotary position embeddings, and alibi. Rotary position embeddings actually learn position embeddings. Alibi just adds a bit of a bias to, the attention operations of things that are further apart. We use alibi at Mosaic because it's a little bit faster. You don't need to really change anything about the network. You just need to, plug in a little bit of a bias into the attention operation. There's no real problem with that. Rotary embeddings do slow things down a little bit. Rotary embeddings do tend to be a popular choice, or ROPE. Whenever I say rotary embeddings, I mean ROPE here, rotary position encodings. The Llama models used ROPE. I think the folks at Adept AI mentioned that they used ROPE for the 8 billion parameter model they released a little while ago. And so, it's a choice that I don't think really is settled right now. We used to say that alibi was really good at extrapolating. Alibi automatically gives the model the ability to kind of look at longer sequences than it was trained on. But now there are lots of interesting ways of also interpolating to get extrapolation with rope embeddings. So it's a little bit of a mixed picture there. Okay, next up is the activation function. This is also a bit of a mixed picture. You see people using all sorts of different things. You see ReLU, just kind of a standard rectified linear unit. You see gated linear units, which actually kind of have their own, I think of it as almost an attention operation inside the activation. Then you have swig-glue, which is gated linear units but use the switch activation. There are a lot of different choices here. And again, you see many different choices in many different models right now. We use ReLU at Mosaic. I believe that the Llama models used a different, I believe they used swig-glue, but I may not have gotten that exactly right. And there are a lot of different choices here, a lot of different received wisdom, but no real definitive answers as far as I've seen. Okay, then you get to optimizers, and Atom is the typical default optimizer that people tend to use. But there are a lot of challenges with Atom, mainly that it just takes up a lot of memory. You need 2 full copies of the model in terms of memory, just because you have to fit in the first and second moments as you're training. And so there have been a lot of other optimizers. There are 8-bit variants of Atom that kind of reduce the memory by half. There's an optimizer called Lion that came out this spring that also kind of has some of those behaviors. Another optimizer called Sophia that came out that claims to be better. There are a lot of different choices here, and I don't think there's a definitive answer. My recommendation when there aren't definitive answers is, choose something that's popular. Look at what we did at Mosaic. Look at what our friends at Meta did for the Llama models. And, those are reasonable choices that are pretty battle tested. If it was able to produce a good model, it's something hopefully you can believe in and stand by. So, that means rope or alibi. Llama used rope, we used alibi. ReLUs are fine. Atom is fine. There are a lot of different choices. The last part is the tokenizer. So I'm not going to spend too much time on tokenization today because I could probably talk for years on tokenizers, and I'm not an expert in that, and the experts could probably talk for even longer. Tokenizers are, how we translate actual text into individual discrete tokens that the model can process. And there is a whole art and literature to this. This is a very big, meaty topic in the NLP world that people have spent a very long time working on. There are lots of different tokenizers. Byte pair encoding, or BPE, and sentence piece tend to be the 2 most popular from what I've seen. And you can train your own tokenizer that is use a tokenizer to develop its own kind of vocabulary on your data, or you can use a generic off-the-shelf tokenizer like the GPT Neo X tokenizer, developed by the folks at Eleuther AI. There are pros and cons to building your own tokenizer. Building your own means that you're taking the risk that maybe your data doesn't represent what people are going to use the model for, and your model may not be as efficient or as effective at processing that kind of data. There are benefits, though. If you're dealing with code, for example, the kinds of tokens you get with code are very different than the kinds of tokens you get from natural language text. You'd get, if and for and curly braces and things like that. It also helps a lot if you're dealing with a language that is not well represented in existing models. If you're dealing with a non-English language, essentially, the kinds of tokens that you're going to want are probably going to be very different, or the vocabulary that you're going to want is going to be very different. And it might help to train your own tokenizer. The ask that I make is, if you're going to train your own tokenizer, it is a messy, difficult art. And I strongly recommend comparing anything you create against a good general purpose tokenizer like the GPT Neo X one, just to make sure that you actually did a better job. Certainly it's a very difficult thing to do, and not all the tokenizers we've created at Mosaic are actually better than the generic one. And so you need to evaluate your models. It's also worth keeping in mind that if you change your vocabulary size, and even if you change your tokenizer, loss is not necessarily going to be comparable between 2 models, so you do need to look at downstream metrics. I want to pause here again for any questions about, architecture and design choices in building an LLM.
This has been super helpful. I was actually planning to ask about what would be your default recommendations, but I like this popularity rule. Just pick what most frameworks are using.
Yeah, pick what has been proven to work. I kind of think that unless you have a huge amount of GPU sitting idle and you can go and test this all for yourself, the best thing to do is it worked for Llama, works for you. Worked for MPT, works for you. You're not going to do worse than those models. Maybe there are better choices out there, but Llama's a pretty good model. You can't go wrong if you follow what they did.
Maybe one question, because I think for the vocab sizes, I've seen a really broad range from 28,000 tokens to 128 or even more. Do you have any good heuristic on how to choose the vocab size?
It's a little tricky because the vocab size will impact the efficiency of the model. And so, you need to, bigger vocabs will be less efficient, but bigger vocabs mean you have more tokens and you may be more token efficient. That is to say, a piece of text may fit into fewer tokens and kind of get back some of that inefficiency. There's a lot of debate OpenAI, from what I understand, tends to go with very large vocabularies. Other folks I've worked with like very small vocabularies. In some sense, it is in the eye of the beholder, and that's something that I don't think has really been definitively studied, and it probably varies by domain quite a bit. So the answer here is like a standard 50,000 or so tends to be pretty popular. I don't think you can go wrong with that. But I have seen, down to 25,000 and up to over 100,000 before in production. And none of them have been like make or break in terms of making a model much better or making a model much less efficient. I think somewhere in that range, you can make a very safe choice.
Thank you. Maybe one more question on optimizers. I've heard like some people considering SGD for training or fine-tuning LLMs because it doesn't have this memory overhead of Adam. Like, do you have an opinion if SGD is a valid choice as well?
It's complicated. I've certainly tried SGD for pre-training and it has not gone well. My experience as a computer vision researcher was always that kind of you use Adam when you don't have a better choice, or you don't know of something that's more specific for the problem. In vision, they used to use Adam until we had batch normalization, which smoothed out training and reduced a lot of the instabilities. And then everybody switched to SGD, and SGD tends to outperform Adam in well-tuned settings in computer vision. For transformers, I sometimes wonder, is Adam the right thing? Or maybe we haven't gotten training to be well-behaved enough that we can use something more specific. So I think it's an open question. When it comes to fine-tuning, I don't really have any clear guidance there. I think it is going to vary setting by setting. It's hard to go wrong with Adam. If you really sat me down and said you get one try at this and you can only do one thing, I would say, okay, I'm doing Adam. But if you have multiple tries and you can play around a little bit, optimizers can make a huge difference in terms of quality of results. After all, a trained neural network is just solving an optimization problem. So, different solution, better solution, they are out there. So it really depends on your budget and how much risk you can take.
Thank you. I think we can go on. This has been super helpful.
Awesome. So then you train the model. And all hell breaks loose. And I say this a little bit tongue-in-cheek, but also especially in pre-training, there are lots and lots of stories out there and a lot of experience that I've lived through where pre-training has just gone horribly wrong for reasons that people don't always understand. You often see loss spikes. And, I'm showing you a couple of examples here from internally at MosaicML, where, suddenly, unexpectedly, loss jumps up, and sometimes it comes back down, and sometimes it catastrophically, you can look at this model on the right, it just kind of catastrophically kills the model. It's a big problem. I will also note experiment tracking. I just want to give a shout out quickly because somebody asked about it. We do use weights and biases at MosaicML, and this is a weights and biases event. These screenshots are from weights and biases where I went and found some models that had loss spikes and took some screenshots of them. So there are lots of different ways to address loss spikes. There's some algorithmic ones. One of the most popular ones you'll see in the literature is simply roll back to a checkpoint, change the random seed, maybe change the learning rate, lower it, and then try again. That's, that tends to be kind of the state of the art in some sense from what I hear people describe in a lot of practical settings. There are other proposed approaches and a lot of research going into this topic, but I do think it's kind of, it is a tricky thing and it does bedevil, especially, I think in the single digit billions and above, you are going to run into loss spikes if you're trying to push your learning rate high enough to get state of the art results. Next thing I'll mention is hardware failures. A lot of GPUs die. This may sound obvious to some people and it may sound surprising to other people, but GPUs die pretty frequently. Or GPUs run into different issues. I have great stories about all the creative ways that GPUs can die. And I think I lost a slide here, but what I was going to talk about here is that there are really a bunch of challenges when you lose a GPU. The first is that once you lose a GPU, the training job dies. We haven't built fault-tolerant ways to train. And so your training job dies, and what do? You just have to resume from a checkpoint and pick up some more GPUs that are alive and keep going. There are a lot of challenges here in even detecting a dead GPU. I've seen situations where the GPU isn't dead. The GPU is straggling and running slowly. And you have to detect that and then get rid of that GPU and keep going. The GPUs also die in groups of 8 because on all the major cloud providers, they're soldered to the motherboard, 8 to a motherboard. This is how you get the fast, multi-GPU kind of, multi-node interconnect that NVIDIA provides or that any provider, offers you. And so, you You can't really just swap out one. You have to swap out a whole board or leave out a whole node. The next big challenge here is that you got to pick the size of how many GPUs you're dealing with very carefully, because let's say I'm running a job on 512 GPUs and one GPU dies. My job may not fit anymore. If I split my checkpoint into 512 pieces, how do I even resume? If I picked my data set around having 512 separate workers on it, what do I do when I lose a GPU? I may lose determinism if I try to resume on 511 GPUs or 504 GPUs if I lose a whole node. It's really nasty because as your training jobs get bigger and bigger, it's more likely you're going to encounter a GPU failure. There are just more opportunities for that to happen, but there's still no fault tolerance. So it's your most expensive, highest risk jobs that are the ones that are most likely to confront a GPU failure just by probabilities. And that's really, really challenging. So what do? I have a few pieces of advice here because this is a persistent problem for us and in general. First is there's a lot of work you can do to automatically detect failures. You can look for NVIDIA errors. You can look for kind of the failure conditions, like the job suddenly gets really slow, and identify those proactively, because a lot of the time your job won't just crash. It will just get really slow or get stuck somewhere. And oftentimes the error messages can be pretty cryptic if you just look at what prints out on the command line and aren't monitoring the GPUs. It also tends to be helpful to keep spare GPUs available. I generally never train with a full cluster. I'll always keep a few GPUs on the side so that I can swap them in as necessary. And you can still use those GPUs for low priority work. You can still get things done on them, but they'll just get taken over if they're needed. You can use sharded checkpointing. So one thing I forgot to mention before is that the other problem with resumption, your checkpoints are really big. We can do some math here, but just taking optimizer state plus GPU or plus model, that's 6x the number of parameters in terms of bytes. So if I have a 100 billion parameter model, that's 600 gigabytes. That is huge. In fact, in many cases, that may be too big to fit into memory on a single node, depending on how big your memory is. But it's also very tricky because it takes a long time to save that to storage and to load it back from storage. PyTorch has introduced some really great support for sharded checkpointing, and we've taken advantage of that in our Mosaic work, so that you can split the checkpoint up into, if you've got n GPUs, you can split it into n pieces. And so that way each GPU can use its network bandwidth and storage connections and save much more quickly and load much more quickly. That tends to help a lot. And the last piece here is that, there are data loaders that provide random access. Again, if you load from a checkpoint, you may end up having to spin all the way through your data loader to go back to where you were. And, we have a data loader that I mentioned last time at Mosaic that allows you to just have random access. And our data loader actually will do deterministic training, even if the number of GPUs changes. And we have, what we call elastic sharded checkpointing, where you can actually have a checkpoint sharded for, let's say, 512 GPUs and resume it just fine on 504 GPUs or whatever other number you want. So there are a lot of mitigations, some of which are built in the software, some of which involve monitoring hardware, some of which are just best practices, but it is something you need to be very careful about. And then you fine tune. So we get to the fun part, we fine tune. I'm going to say just a little bit on this. So someone asked about fine tuning versus instruction fine tuning. RLHF is in there. And I kind of left the slide blank to answer any questions that we had there. So I'll clarify a little bit and then put out a call for questions. But the way to think about fine tuning is that you're taking a model and you're training it and using it for some other purpose. That purpose may be more specific. It may be a particular domain, like fine tuning a model for code, maybe a particular task like classification. It may be some other paradigm. And what tends to be popular for general purpose chatbots is a process where we start by fine-tuning for anything. Fine-tuning is kind of the umbrella term. And one thing we might do is what's called instruction fine-tuning or supervised fine-tuning, SFT or IFT. SFT is becoming more popular, so I've started switching to that. And the idea is that you have a lot of example interactions with the model, a command or an instruction, and then a response. And all you're doing is you're kind of training the model to see its first part of its input as an instruction and then respond to it. Because naively, the model is just trained to spit out documents. It's trained to just kind of continue generating tokens, and giving it some examples of instructions and responses is really helpful. And I mentioned last time, on the order of tens of thousands, will get you into the ballpark of Llama 2 in terms of what they did, as long as they're really good quality, and quality matters. Then there's a process called RLHF, and I'm going to say a little more about RLHF. Hugging Face has this beautiful blog post on how RLHF works, and I recommend reading it, but I stole a couple figures from it. And the idea is that, We can ignore the RL part. I think almost, there is RL going on here, but I think it overcomplicates things in terms of understanding. All you do is you take your language model, you generate some outputs with respect to some prompts, and ask humans what they think of them. Was this good or bad? Was this one better than that one? How much better was this one than that one? And then you train a model to predict a score for each response. Like, how good was this response, or how good would humans say this response was? And then you go through this more complicated process. This is the RL part, so I'm not going to dwell too much on this. But all you do is you essentially train your model to, to maximize the reward, to give prompts that humans would give high scores to based on this reward model. You can also, you'll see this initial language model over here. You can also kind of, you don't want the model to stray too far or kind of get too, get too obedient in some sense, or kind of, try to max out the reward. So you can also constrain the model to behave like the initial language model a little bit so that it doesn't change too much. So, that's the RLHF process. And the idea with RLHF is that you're trying to get the model to align better with human preferences. When people talk about alignment, this is often the technique that they're looking to use. The last thing I'll mention is LoRa, because LoRa tends to always come up in the context of fine-tuning, and I didn't want to go without mentioning it. So when you fine-tune, often what happens is you're modifying the weights of the whole model. But not all of us have a big fancy GPU where we can fit all the weights in the model. And sometimes we want to have many, many different copies of the model fine-tuned for different things. This is where LoRa comes in handy. All LoRa is a way of kind of, you learn this thing on the right. You've got your pre-trained weights on the left, and you learn a modification, a delta, a change to those pre-trained weights. And that change is actually, you would typically have to have a matrix as big as the matrix representing your weights. But in LoRa, you split up that matrix, you factorize it into two kind of low-rank matrices that you can multiply by each other to create one big matrix. The idea is that this does give you a way to change all the parameters in the pre-trained weights, but it takes up a lot less memory because you don't have a full additional copy of that matrix, just two much smaller tensors. So it's lower rank. It doesn't allow you to change, it gives you a limited basis on which to change the weights, but LoRa tends to work really well in practice. And so it tends to be pretty popular, especially if you're at home and you have a 3080 or, some older GPU that doesn't have as much memory, or just a gaming GPU in general. LoRa tends to be a lifesaver because, you don't need to store that much when you're doing the forward and backward pass. Just the LoRa weights plus the main model. You don't have to do a backward pass and store a second or third or fourth copy of all those weights, or optimizer state for all those weights, just for kind of these orange weights on the right. That saves you a lot of memory. With that, I'm actually going to pause and see if we have any more questions. That is all the content that I brought for you today. So, I'm happy to chat from here.
This is awesome. Thanks a lot, Jonathan. So one question I have, since you show this loss charts from weights and biases, it's like the most obvious metric to monitor, but is it sufficient? Like in practice, either during training or fine tuning, do you have other ways of evaluating if the model is improving, if it's worth to train it longer, or is loss sufficient to make that decision?
Loss is definitely not sufficient. When pre-training, loss gives you a really good directional sense that you're making progress, and it does tend to correlate with other metrics. But once you get into fine-tuning, loss tells you almost nothing. So I mentioned this a lot last week, but I guess it's worth really emphasizing this week as well. Evaluation is where it all begins. You have to know what you're measuring and what success looks like, and it has to be on a downstream task. Loss is not enough. Your objective is not enough. So, I'll just emphasize that. I know you know that, but, for everybody else out there, just as a reminder, evaluation is where everything starts. And until you know what you're measuring, don't even get started training, because you don't know why you're training.
Thank you. I wanted to ask this question, like with a limited budget for fine tuning, like would you recommend people to go for a bigger model, for a smaller model, and like fine tune all of the parameters, or would it make more sense to take a bigger model and do like LoRa or QLoRa or any other methods? Like what would be your like default approach here?
So it depends on what your budget is. I want to emphasize LoRa is really interesting. I know we talked at the beginning about, the actual speed and the, and the memory usage. LoRa will dramatically reduce your memory usage. LoRa will not help your speed very much. The reason being that you have to still forward propagate through the whole network, all the weights, and you have to backward propagate through the whole network all the weights, and then update the LoRa parameters. But you still have to do that chain rule. So LoRa, we found, doesn't save you very much in terms of training time. It will save you some memory. So if you have a low memory GPU, it's really, I think LoRa is super popular for two reasons. One is that if you want to like very quickly swap out multiple models, LoRa gives you a very convenient way to do that. And if you have a gaming GPU, LoRa is a great way to be able to fine tune something really big. But LoRa is not going to be any cheaper. It's not going to save you any cost. So at the end of the day, it really comes down to what your budget is, and LoRa is not going to rescue you in that respect.
We have another question from the audience. What are the scenarios when fine-tuning makes more sense than, for example, prompt engineering or training from scratch? Do you have any
I'm going to go back to
for that?
I'm going to go to my friendly advice page because this is where I go for everything, and this is going to be friendly advice piece number 1. Start small and work your way up. Start by prompt engineering. If that gets the job done, great. If you can't get the job done, then explore fine-tuning. If fine-tuning gets the job done, great. If fine-tuning doesn't, then we need to talk about pre-training or whether anything can solve your task. But, I always instruct people, start small and work your way up. Even though a lot of our business at Mosaic is training the big stuff, I don't want anybody to waste their money. If they don't need to train the big stuff, they shouldn't. And so my answer to you is try it and see, but start with the easiest thing first and the cheapest thing first.
Mm-hmm. We have a question about how to think about designing evaluations for downstream tasks. I think we covered this a little bit in the previous lecture, but you mentioned this is like the critical topic, how to do evaluations. I thought it's worth sharing that question again.
Yeah, I direct that person to more of what we talked about last time, but what I will say is it is the most critical topic and the thing we understand the least. We know so little about evaluation and how to evaluate properly. It's something where there aren't really best practices in the field. If you have a process you're already integrating a model into, however you would measure success for that process, measure the model in the same way. But otherwise, it's incredibly bespoke, use case by use case. And I wish I had general advice, but the general advice is try to get it as close to the real world as possible. And the rest is kind of up to you as the domain expert.
Thank you. And then maybe a question from me, like we've learned a lot from you throughout like this lecture and the previous one. In the previous one, just as a reminder, we covered data. And today we learned about different techniques, including both like choices of architecture, of fine-tuning methods or training methods. And if let's say I have like a limited budget or limited time working on an enterprise use case, like how much time should I allocate to each of these buckets? Should I spend more time on the data front, and just go with the defaults for all of the training techniques, or should I spend more time, like with the given data, just focus on squeezing more out of the model? Like, what would be your recommendation here?
Oh, this is so hard. It's very scenario specific, so it's hard to give advice. What I tend to do is I like to kind of round robin a little bit, get everything to the point where I can get something end to end, spend a little time on data, a little time on modeling, just get something minimally working. And then you can start improving and optimizing. But I think the biggest mistake you can make, the thing you should not do, is spend tons of time on the data and then go and train the model. You need a way to measure whether the changes you make actually matter. And so once you have a minimal model and a minimal data set, you can measure like this easy thing I did to tweak the data set, did that help meaningfully or not? This easy thing I did to tweak the model, did that help? And you can figure out where to invest your time and resources, where you're getting returns, what is working, what isn't working. But I think the most dangerous thing would be if you did a deep dive into one of these before you had something end-to-end working and you could evaluate your success. Again, it really, in some sense, it does go back to start small and work your way up and test for yourself. It's all about spending your time, money, energy as efficiently as possible, because this is so expensive and you can go down so many very deep rabbit holes.
We have another question, and this is very specific. Would you recommend using FP16 or BF16 for training?
BF16. BF16 is a slightly different floating point representation than FP16 that shifts around a few of the bits in, between the exponent and the mantissa. I can never keep track of which is which. but BF16 tends to be a little bit more numerically stable for the kinds of scenarios we see for training in practice in FP16.
Hey, let me check if there are any questions left that we have not answered yet. Yeah, we have this question, which I think it will be like a really good question to finish with. And the question is about this point from the slide. If you can expand on it, this is data science in its truest form. I think I remember you talking about this in the previous lecture, but I think it makes like a perfect conclusion to this series.
Yeah, I completely agree. So, I always heard the term data science and I never really thought much of it. I thought it was a little bit of marketing. I'm a data scientist. What does that mean? But, this is really when I look at deep learning and in building anything, you have to be a true scientist. You have to pose hypotheses, run experiments, build knowledge for yourself about your situation and about the world. There are a lot of experiments that have never been run before. And chances are when you're building a network, you're going to run an experiment that nobody has ever written about before to understand, like, should I use this activation or that one or what have you? And so you have to be a scientist. You have to embrace that empirical scientific frame of mind. Everything is an experiment. Everything is a scientific question. And your goal is to generate knowledge that will be useful to you. So I kind of think of this feels like when I hear the word data science, that's what this feels like it is. This is really being a scientist in the same way that a physicist runs experiments or a biologist runs experiments. It's the same thing. And so, I think the thing I want to leave people with is really be critical, think for yourself, and be a scientist. Every situation is different, and we know a lot less than what we don't know right now about deep learning and LLMs in general. So chances are, for a lot of this, I didn't even give answers. I didn't tell you what to do. I just kind of described what's out there and the choices and the trade-offs because I don't know what the right answers are in general or for you. So, that's really, you're going to have to be a scientist. And I'm not going to have all the answers for you. Nobody will. Figure it out for yourself and good luck.
Thanks a lot, Jonathan. This has been both super educative and also inspirational. So I appreciate you investing this time, sharing this knowledge with the community. It's been a great honor to be learning from you, and I recommend everyone to follow Jonathan, follow MosaicML and Databricks. I know you're training fantastic models, and it's a great service that we can recommend. And for everyone that joined us in this series, we appreciate you staying with us, and we hope you get to train and fine tune LLMs that meet your needs, meet your business needs, that score high on whatever evaluation you've chosen. And for any questions and ongoing conversations, we recommend you join our Discord, and we'll post a link to the Discord below the video, wherever the video is posted. So thanks everyone. Thanks a lot again, Jonathan. It's been great pleasure to be learning from you.
Thank you so much.
Have a great day, everyone.